Welcome, everybody, to the last installment of the California Dreams Technical Seminar Series for April. We are very happy to have with us today two speakers, so it's a little bit different kind of seminar for today. Today we have Steve Zamek from PDF Solutions. Steve is the Director of Product Management at PDF Solutions, responsible for their big data analytics platform, deployed with many important customers. He's got a PhD from UCSD, so all within the hub. And our second speaker is Brian Thibeault from UCSB. Brian is the director, the technical and operational director of the UCSB Nanofab that is such an important part of our hub and has been so successful. He's been in that position for 6 years. He's been at UCSB about as long as I've been at USC, since finishing his PhD in 1997, although he had a break working with a startup company that got acquired by Cree in June of 2000. So we're very happy to have both Steve and Brian with us today, and I'll turn it over to Steve to get started.
Thanks, Steve, for the introduction. So without further ado, let me get to the content. So before I discuss the big data analytics, I will do a quick introduction of the company. We are a public company, founded a little over 30 years ago in 1991. We have about 600 employees, and the revenue from our analytics is about 90 million a year. We strive to provide solutions across the entire spectrum of manufacturing, including fab and foundry, sort assembly, and all the way out to system level test. So in this talk, I'm splitting the virtual stage here with Brian. I'm going to cover 3 topics: data analytics for semiconductor manufacturing, discuss the data types used, and then explain how we support a variety of different fabs, including Megafabs and all the way to Nanofabs. And in Brian's part of the talk, he's going to focus more on the Nanofabs and how they've been using the analytics for their use cases. So this shows a quick overview of the suite of our solutions, software solutions. They are structured by the different market segments. So you see that we have something for everyone. The abbreviations here: AO is assembly ops, PC is process control, TO is test operations, and MA is manufacturing analytics. So MA is the general platform that is at the foundation of what we are going to discuss. So I'm going to cover that in the next several slides. And then, of course, to get all the different data types from the different types of facilities, you need the connectivity layer. And so here we have a variety of different solutions, because as it turns out, every type of facility has stringent requirements, and it requires a particular type of connectivity. I also want to say that we provide the services, and that's how the company started. So CV stands for characterization vehicles. So historically, our company has been doing a lot of yield ramps, and we have a history of doing over 60 yield ramps of fabs around the world. That actually gave us early on a great insight into all the manufacturing flows and all the different data types. And some of those solutions were initially established for internal use, but today they are offered as a product. Here you see an example of the various customers that attend our user group conferences. We also have software that we provide to capital equipment manufacturers. There are about over 200 equipment suppliers that use our software. However, that is going to be outside of the scope of this talk, and we're going to mostly focus on the manufacturers themselves. So first, let's discuss the data types used in the different areas of manufacturing. So as you go from wafer manufacturing through assembly and test, all the way out to final test, every area of manufacturing has its own data types. There is a legend with abbreviations here. I will only cover a few important ones that I'm going to discuss in the next several slides. So in the wafer manufacturing, MES is the manufacturing execution system. That is the system that orchestrates the operation in a fab. It keeps track of all the different materials and wafers and lots and other entities, where they go, what is the track out time, and a lot of other attributes. C of A is certificate of analysis. This is the type of data that you get for material that enters the fab. For example, wafers, epi wafers, and other materials, they are provided with a C of A. There is a genealogy that explains the relationship between lots. Lots go through lot splits, regrouping, rework, etc., etc. So the genealogy tends to be a very important data type. Equipment logs and traces. Every equipment, as I'm going to explain in the next slide, has a variety of sensors, and that is the data that is being collected. And then also, of course, there is the inline data, such as metrology and inspection. There is also electrical characterization that is done using PCM structures or electrical wafer sort, and I'm going to cover that as well. Overall, there are terabytes of data per day in any of those megafabs, and the data retention requirements are such that you end up with petabytes of data. Now, operating on such a huge volume of data and being able to extract meaningful insights and capture any excursions in yield or your performance, that's where the big data analytics comes in. So MES data, in the next 3 slides, I'm going to cover the key data types. MES data for manufacturing execution system, it has things such as wafer equipment history and lot equipment history. The material is handled in cassettes or FOUPs, and those get dropped into the different tools. And in each tool, it goes into a particular chamber. Tracking the wafers by wafer ID creates a full flow, including all the different steps that the material went through. The other data type is raw traces. Every manufacturing equipment will have anywhere between 100 to 200 sensors on the tool. This is going to be anything from temperature, DC bias, RF power, voltage, temperature, you name it. And all that data is collected at a high rate, 24/7 without stopping. And so being able to analyze the data is definitely very important. So you can get this data at the level of a particular sensor, or you can get a very highly aggregated data at a tool level and only keep track of the excursions in the data. Next one is metrology. Metrology typically is done on targets, special metrology targets placed in the scribe lines. There are 3 specific types of metrology: shape, where the targets are used in order to characterize the complex geometry. There is a CD for critical dimension. Typically, very early in the process, you put down the transistor gates as lines, and CD actually gives you an early insight into what you can possibly expect from those transistors. And then there is an overlay. Overlay is very important because there are thousands of steps involved in the process and many patterning that happens, that every pattern needs to be aligned to the pattern underneath. So overlay is the metrology type that is also very, very often used. PCM. So by the time you are getting close to finishing the wafer in the fab, you typically have the ability to probe. And so you do some preparation to enable electrical probing. PCM are the structures for process control monitor that are placed in the scribe lines. And using those structures, you can get a good idea about the performance of your process with respect to things like threshold voltage, leakage, transimpedance, and many other things. This is very important data type because that is the kind of data that is shared by the foundry with the customers, because it provides a very good insight into where you are with respect to your process window. And this is probably the most prevalent data type, electrical wafer sort. The reason it's so prevalent is because it's used by almost any manufacturer, whether you are a foundry or fabless company or outsourced assembly and test facility. you're going to be typically dealing with this data. And because the testing has to happen for different loading conditions and different environmental conditions, it's very common to get a huge amount of data for both bin and parametric characterization of the dies. There is also virtual operations. So based on many different steps in the testing and many test insertions, you typically apply some transformations and spatial outlier screening, and you generate a map that is going to be used for deciding which die you're going to pick and use in the assembly. So this shows you the example. I covered so far only a few data types, but in fact, there are dozens of different data types in manufacturing. And here you can see the tracker of the different deployments that we have in some key customers. Here, every row in the table represents a specific customer, and every column in the table represents a particular data type. So you can see that the deployments are unique. Every customer will decide which kind of data it wants to integrate. However, what's common across all of those deployments is the data model. The data model is what describes the relationships between the different data types and puts it in the context. So how do we do it? This slide kind of covers a little bit under the hood. All the data gets loaded into the platform. This shows you the architecture of our platform. At the very bottom, there is a connectivity layer. There is typically a combination of hardware and software that enables you to collect all the data. And it differs between the different data types and the facility type. And here at the very top, you have the application layer, including some very advanced AI and ML analytics. Here in between is very important. There is a middleware layer, and the middleware is what actually allows you to clean the data, enrich it with a proper context, and then align the different data types with respect to each other. So overall, we do not operate in a vacuum. There is a variety of different APIs, because in a typical facility, there is a variety of different software tools and a variety of different databases, and you definitely need to be open to those integrations. So definitely need a strong set of connectors and APIs. And just to give you a little bit of an idea about the complexity, operational complexity at some of those customers that use the big data analytics, here you can see the example of a device manufacturer. A device manufacturer will typically employ a combination of both internal and external sites. For manufacturing, it will use a variety of different suppliers. Even for the same material, it will typically use multiple suppliers. And you can imagine that with the multiple internal fabs and the multiple external foundries, you end up with a huge amount of data that comes in a variety of different formats. And it definitely creates a big challenge, which our platform addresses. So I'm going to switch gears now a little bit and talk about the analytics platform for nanofabs. Everything I described above was mainly geared towards large facilities. But in this engagement with university nanofabs, it's quite different. So here you can see the example of the process maturity and technology readiness level, where on the very left, you have the facilities that have very little analytics and very little maturity, operational maturity. And here at the right, you have the facilities that are able to predict things and act on things before they actually happen. And what's very interesting here is that traditionally we've been really focused on the facilities on the right, which are the commercial fabs, anywhere from 6 to 12-inch fabs, including the most advanced ones with a huge amount of automation. But for the purpose of this project that Brian is going to talk about, we actually made some big strides in engaging with the nanofabs, where we are facing a whole different set of challenges in terms of deploying our analytics. But overall, based on this engagement, I can say that we are deployed at this moment across the entire spectrum of manufacturing. So a little bit about the California dreams. as part of the Microelectronics Commons program. This is a slide I borrowed from Dev Shenoy. It basically explains the university, fabs, and prototyping facilities and the target commercial fabs. You can see here the valley of death. The valley of death is where a lot of the technologies die on the vine. Definitely there is a need to facilitate the transfer, the technology transfer from universities to the target fabs. And so what we are doing in that program, we are improving the operational efficiency of the nanofabs, improving the process capability and repeatability, and accelerating the technology transfer. How do we do that? So we started with a very aggressive roadmap that spans 5 years. It's a 5-year journey. And in the first year, we actually deployed the analytics across 6 edge tools in 3 different sites, UCSB, UCSD, and USC. In the second year, we are adding 12 additional tools in 3 different sites, and we are also expanding to cover a lot more recipes and a lot more use cases. So right now we are in the middle, we are actually past the middle of the second year. And I want to say that so far it's been very successful. You're going to hear more about this in Brian's talk. I'll cover this very briefly, how we are actually doing it. So the universities, those nanofabs, are responsible for collecting the data on site. They put it in a shared folder. We load it into our data platform, and then we use a variety of different analysis templates to provide the tools and put those tools in the hands of the staff in those facilities. So by doing so, the staff in nanofabs, they have full visibility 24/7 into what's going on with the tool, down to resolution of any particular sensor on the tool. And that, as you're going to hear, enabled successful root cause analysis on a variety of issues. So I want to acknowledge the great work by the team here. We have a lot of collaboration between the 3 nanofabs. We are very engaged, all of us together. It's been a joint effort, and I want to acknowledge here the 3 facilities where we are deployed: UCSB, UCSD, and USC. Definitely UC Santa Barbara has been leading the pack, so I'm very lucky to have Brian here continue to the second part of this talk. And we've been working very closely with our stakeholders, which are the defense industrial base facilities, where the intent is that some of those technologies developed by the nanofabs are eventually going to be transferred to those companies. Thank you, and I'm going to mute myself and hand it over to Brian.
Thanks, Steve. That was really great. So I'm going to start by giving a little bit of an overview of our facility and in particular how we gear ourselves around helping our external customers and in the midst of our really very vibrant small business community that we have here in Santa Barbara. Oops. There we go. So first, because our mission really is to serve UCSB and the greater community and in their research and development endeavors. And the way I like to think about it is we want to enable the highest caliber of research, but at the same time, we want to enable impact beyond the university walls. We don't feel like we're doing our job if the technology that's being developed here isn't making it outside and making an impact to the greater world. So we strive to provide exceptional resources and professional and technical expertise to support both our researchers here and our many small company users and other even large company users that use our facility for development. So what are we? We're an open access user facility here. We've been operating for over 25 years very successfully. We have about $60 million of equipment, and we have expert staff support for processing and for equipment repairs and service and customization. And so we're here again to support innovation and product development. We have about 500, it varies a little bit year to year, but I'd say right now it's about 530 annual users, and more than 40% of these consistently are from industry outside. Most of these are from small companies that have formed in the area based on the technology that is prominent here at UCSB. We have about 5,500 to 6,000 hours a month billed in this facility, and more than half of those hours are industrial, just giving you an idea of how busy our fab is. And this is, to our knowledge, we're really one of the largest, or maybe the largest industrial base, nanofab that supports from any university in the United States. We've had 75 local companies actually use us since 2006. I'm going to show another plot later, that a map. And how do we run this? So we run in the black. So we're a self-sufficient operation. And the way we do that is by supporting our industry use as well, and by supporting that technology transfer. So we have a tiered rate structure where our academic folks get the benefit of being able to use our facility at a low cost. And our industry folks, they pay a higher rate, but it's at a rate that's that's very, very competitive for the kind of equipment that they get access to. It's a win-win situation, is the way we like to put it. Just a snapshot of the kind of things that we have in our facility. So we have deep UV lithography, which is pretty unique for universities. There are only a couple of universities that have this capability, and that's the 248 nanometer system that gets us down to 150 nanometers. We have EBL, a variety of etchers, SEMs, ALD systems, etching systems, sputtering systems, rapid thermal processing, characterization. We have the whole suite of semiconductor fabrication equipment. Everything's built for 100 millimeters or more. We can really support everything at 100, and we can support many things at 150. And we have a wiki that describes everything that's accessible for everybody. And we're continually trying to upgrade and improve. That's something we're always trying to do. And just an example, we've had 2 new SCMs we installed in 2024. We have our new EBL, which is going to be opening up next month. And we have a new maskless laser lithography system for rapid prototyping coming in June. And this is just some more, I like to call eye candy of the kinds of work that historically gets done in our facility. So the facility is very well known for pioneering work in gallium nitride-based hemp technology and lasers and LEDs. We've had work in 3.5 MOS and also in terahertz transistors. Some of these technologies in these areas have been transferred to both defense companies and have spun out and have formed spin out small companies. Lots of silicon photonics. The hybrid silicon photonic platform was invented here at UCSB and John Bauer's group, and has since just taken off. Many companies are formed by that, and many companies and foundries now are using this kind of technology in their processes. And we have quantum and qubits and microfluidics, and we really support the whole range of technology here. We try to make access to the facility simple, quick, easy. We believe that customer service and being able to support people who need access to this equipment so they can do their custom development work that they need to do before they can demonstrate things for Foundry. We try to make it simple set of paperwork. Our initial orientation and training is about 5 hours. We train technicians and engineers on systems as needed, and everyone gets access to consultation support from our staff at any point in time. We have expert staff that can perform fabrication work for people, so we do things on a remote basis. That just requires a small separate service agreement, and we're also now set up to do work for Moses 2.0 for any kind of custom work that they might need done. Our real goal is if we have users come to use our facility, we want them in and working within a week if we can get it. That's paperwork, everything signed, everything agreed upon, and initial training being done. Okay, we also have additional support at the facility through consulting groups. They're experts with our tools. They've been using our tools a long time. They have very good relationships with the staff, and they can really provide a lot faster direct fabrication support. And that's been very lucrative for some people who've used our facility. We really do impact a lot of the state and even the nation. We consider ourselves a real strong state and national resource. Most of our work, of course, is local, but you can see we have clusters in Southern California, clusters in the Bay Area, and we extend all the way out through the United States and the people that we serve. Just in California alone, we've served over almost 230 companies. Okay, and many of these are small, and many are local. And in fact, 35 of the companies out here were actually started up from students and professors here at the university. So we have an extremely vibrant small business generating ecosystem here at UCSB. This is a big view of a list of the companies that have used our facility, with those in bold being our local companies. Ones. And here's a snapshot of some of the success stories we've had for some of the small companies. So Atolo Engineering, they've set up a manufacturing site down in Camarillo. They do imaging systems primarily for defense. Sora Laser, which was founded by two professors here, including Shuji Nakamura, Steve Denbars. They developed gallium nitride-based lasers, high-power lasers that were used in they're used for headlights, they're used for searchlights, and other high power lighting applications. And they were acquired by Kyocera, and they're now over a couple hundred employees. Illuma is one of the more newly formed companies here, and they've just recently gone onto the NASDAQ in 2025. Google and the Google Quantum Group that is now established. Has now established labs in Goleta, several of them, and they're up to about 150 employees. And they did a lot of their initial development work on their quantum qubit computers here at UCSB. Freedom Photonics, they took some of the indium phosphide photonic integrated circuit technology and have commercialized those things, and were recently bought by Luminar for LiDAR-based applications. And they've now moved a lot of this processing over to Foundry. Transform, which was founded by Umesh Mishra and some other former students. They basically commercialized gallium nitride power electronics. Okay, and they've recently been purchased by Renesas, and so their products are now being integrated into the automotive and other power conversion units within Renesas and beyond. And then kind of a different kind of small company. To show the variety of work that's done here is CMS. They make the highest reflectivity infrared mirrors in the world. These are like crystalline stacks that form DVR layers, and they develop techniques to be able to bond large area semiconductor materials onto curved surfaces like glass and plastics and other things, so that they can make these very, very precise optics that are required for very, very high finesse optical cavities. So it's a very niche market, and they were originally purchased by Thor Labs and are now part of their portfolio. That's just a snapshot of the kind of small companies and successes that we have here. I'm going to go ahead and switch gears now, because that really motivates why we're interested in analytics and in working with PDF through ME Commons. This is a great opportunity for us, and we're excited about it. The work I want to talk about now, I want to acknowledge Fong and Noah and Viraj. These are people from my staff. These are Fong and Noah are process folks, and Viraj is our IT person. And then the PDF engineers have been great, and it's been a really great collaboration that we've had. So some things with the R&D facilities that people may be aware of, but I think it's good to motivate this work. Very different from a large fab or from a commercial fab where things can be more controlled and the same thing being done over and over again. So in a nanofab, we don't have a lot of staff. We often traditionally rely on user-reported errors to address when machines have problems. So we're kind of reactive and not proactive generally. That's not great for reproducibility. And there are a lot of failures because of that from our customers, including our industrial customers. There's often minimal qualifications or calibration runs done on the systems. Again, this because of staffing, it's hard to increase the frequencies of calibrations. Just checking machines for MFCs and leak rates, et cetera, it's not enough to really catch problems and to be proactive. We have a huge mix of materials and processes often within the same systems, not just a big mix. We will run many materials, one right after the other, different ones, one run right after the other within short time periods. So we have high potential for materials influencing each other in our systems. And the reason we have to do this is to run a facility like this, it does cost a lot of money, and so we need our machines to be used. And so in order to have all of our machines to be used, we really have to have a very large diversity of materials and processes running. Redundancy of systems for us to isolate processes, that's expensive, and it's more money than we can really, afford to do in our facilities. Hundreds of different people are going to touch and use and program these systems. It's not just a small team of operators doing work for engineers who are designing things. So because it's also a lab that's used to instruct and to teach and to train the next generation of people who are going to go out and do this work.
Okay.
So we have lots of young users. So it means human errors are also abundant, even with the SOPs that we have in place to try to minimize these things. So with all that said, our goal, and we're so glad PDF thought this was a worthwhile thing to pursue, is we want to try to incorporate SPC control of machine sensors to detect problems, to be proactive, to integrate this into our unique fabrication facility. So we want to correlate outputs of machine sensor values over time. We want to include, like say for etchers, OES. We want to tighten the controls on our systems. We want to determine all the system differences that we have with our outliers. We want to ID the root causes when things are out of spec. We want to be able to provide our customers with assurances of the machine health, that when they put their samples in our machines, they have a good high expectation of getting the output that they want, even in the midst of our very diverse environment. We want to see the drifts over time so that we can look and see, can we find out the causes of these slow variants? Can we make sure that our users are aware of the variances of the machine in the machine drift so that they can compensate for these things? And we want to improve the process transfers from facility to facility. And that's so that, one, if we have systems that are going out, we'll be able to have work done at other facilities because we know they can have equivalent processes. Or when we're ready to transfer processes into Foundry, if we can do some machine matching ahead of time, that makes that process a lot easier. Basically, we want to do everything we can to reduce failures, improve lab development times, and increase our ability to transfer process. So let's talk about some of the results and some of the things that we have done to date here. Steve went over this a little bit, basically how we have set up our system. It is not real time. So what we do is we take our log files, and the log files are then parsed and processed here to a format that can be uploaded into the PDF servers, and then they put it into their Exensio process control program, which is cloud accessible, and then we're able to access the data. It's the machine sensor data plus all of the output data that we have linked to really any process that is being tracked by lot or by recipe name, etc. So we started this in late 2023, early 2024 with 2 etch systems, and that's what I'm going to be talking about. We took all of our historical log files from the systems and we parsed all that data, and so that we could analyze it versus our history and to begin to look at our systems very quickly. And we're working with the PDF engineers. We've learned how to use this software. We can operate the software and set it up and do our own analytics now. Without PDF's direct help, but we still interact with them all the time. Okay. So let me give you a few stories. So this is the first story is about our fluorine ICP etcher and looking at our silicon dioxide etches, which we were calibrating before we start with PDF. We were calibrating at a pretty low frequency. So I'll kind of talk about area 1 here to start with. So we looked at historical data, all this historical data up until early 2024. And we tried to correlate this with all the machine data that we had through using Exensio. And we were not able to really find any correlations. So we thought, okay, maybe we just have limited data. These are like plus minus 10% variances. It's pretty large variance. So we decided we needed to increase our data rates. Okay, well, as we're doing that, in March, we saw a huge jump in the rate at 0.2. This is where the analytics kind of just gave us right away what happened. Taking all the data from high etch rate and low etch rate materials, we were able to quickly, through autocorrelation, find a correlation between our data and the DC bias on the substrate. Well, it turned out that we had replaced a clamp right in here, and we were not really aware of the thickness control required on that clamp in order to, keep the DC bias under control. So we learned that. All right, we were able to fix that. But as we're fixing it and kind of getting back to learning and getting back to where we are, we still saw a huge variance even with the increase in the data rate. And so what that pointed us to, it's not a machine sensor problem. It turns out it points us to looking at measurements and looking at our procedures. So we did that. We tightened all of that up. And when we tightened that up, we saw the reproducibility get dramatically better with our as we went on with time. So without the data and without being able to do the analysis, we always thought that all of our variance was due to machine problems. Really was due to in this case, that was due to procedural and measurement types of problems. So we've tightened that up. We've continued to track and watch. We've caught various small things as they've happened. I'm going to highlight that with a different machine. But we saw also a small drift occur here in late 2024, where the etch rate slowly creeped up, and it turns out that was DC shift correlated and related to some RF tuning circuit adjustments that we needed to make. So there's a drift that happened in the RF side of the system that we really don't fully understand yet, but we were able to track it, note it, and then allow our users, inform them of this and make sure they're aware that they would need small adjustments in their time. So that's, again, it's all about helping. The goal is really about helping our customers to have the results that they expect. The other thing we've looked at, and I'm going to highlight this on our Oxford chlorine etcher in the next slide, but I wanted to show you how we do this. We also analyze outliers. So outliers are things that are going outside of what we consider a reasonable range of specifications for say, etch rate output. So the way we do this is we can take and highlight just the runs that had outliers, and we can compare all of the sensors with good runs that we've had. We can do this very quickly and very efficiently, with a few clicks, basically. And the software actually highlights very quickly the sensors that you need to look at that are different. And we can look at those and decide which ones are important, take a closer look at them. So in this case, we're seeing high etch rate on indium phosphide. And so we went ahead and did the analysis, and we found that right after an ITO etch, what we saw is that the hydrogen signal from the OES is lower in the chamber compared to our normal runs. So that pointing to the fact that ITO is doing something to the chamber walls, it's affecting the chamber chemistry. And so that then pointed us to fixing our cleaning recipes in order to mitigate this problem. So more about outliers, just using that kind of methodology. With indium phosphide, we saw the same things with our indium phosphide etcher, a large variance. We tightened up our measurement and our procedures, and we were able to get to a much tighter control. And then we have these outliers. So for instance, number 3 here, this outlier, this high etch rate. Well, when we went and did some comparison, we found out that from OES, basically, that our intern had forgotten to run a season recipe beforehand in the chamber, which is required, and that led to the high etch rate. Okay. This other one here, number 4, another low etch rate. It turned out that there was a small signal that we detected of the plasma turning off and on during the etch. And so the machine didn't fail, the machine didn't give us warnings, it didn't stop the etch, but we were able to go back and look and figure out what happened. Okay. And then we were able to look at the RF system for problems. And then another one here, which is a large fail. The machine didn't actually fail here. It actually allowed the recipe to continue. Well, it turned out it was another RF issue where the plasma wasn't lit, leading to a very low etch rate. And this led us to find a recipe issue with our monitoring alarm for the DC voltage for the system for the set point. So we fixed that. And then this also led us to see some ignition step problems that we had. We had a couple more failures. So we must have had some machine drift that made our ignition recipe a little less stable. So we fixed the ignition step to move it to a more stable operating point. And from that point in time, we have not had any more failures. So those are some examples of how we've been able to look post-mortem at data in order to find some root causes and point to solutions. We've also been able to help users quickly identify problems. This was a user who brought us this data from mid-2024. This is an indium phosphide-based type of process where they had very nice etching. Same process, same recipes, just different times for the etches, and very similar epi structure, and completely different results. So we were asked to take a quick look at this. We did the quick analysis and found that there was actually a strong DC bias difference between these two runs, even though the recipes and the recipe parameters, all the set points were the same, the RF and the powers, all these things were the same. Why the DC voltage? Well, in this system, people often put wafers on carriers before they go in, and we have two different carrier types. We have silicon and we have aluminum nitride. Well, for this recipe, you have to have a silicon carrier. And it turned out that when we went back and inquired about this, because we suspected it, it turned out that the technician made a mistake and used an aluminum nitride carrier instead of silicon, and it was evident from the sensor outputs. So again, this is just, this helped us to really ID, having these autocorrelation and then the trace views very easily accessible, really helped us ID the problem quickly. And now the kind of the newest work we've been looking at is we're beginning to look at the machine transfer efficiency and trying to do efficient process transfer. So, okay, just quickly so we can have some time for questions. The goal here is we want to be able to transfer processes from one machine to another machine, from one fab to another fab within as few runs as we can. So what we have done is we took two machines, one here, it's an Oxford system, one at USC. Thanks Shiva and Shannon for taking part in this. They're the ones running the USC system. They also have an Oxford system, but it's a different geometry. They have a smaller chamber volume. There's some gas throughput differences. So what we did is we took an indium phosphide etch and we built a DOE around that so that we could kind of get a mapping of the systems. So we know which parameters in one system, how they relate to parameters in another system over a range of parameter space. So based on that, we were able to get, with the help of Exensio and comparing the sensor outputs, comparing the output results, we're able to get calibration factors between the machines. So one set of parameters in one machine translating to a different set of parameters in another machine for recipes. Using this matching, we established a new recipe in our chamber at UCSB here. The chlorine nitrogen recipe and gallium arsenide. We just went ahead and developed a quick recipe. And using that mapping, we then sent the material and the equivalent recipe parameters over to USC to do. And with one etch, we actually amazingly got very similar etch rates and mask selectivities, basically using this matching type of technique. Now, we didn't do this matching perfectly this time and made some mistakes, and we're going to work on improving that methodology so that we can, and we're going to apply this to some other systems and materials as well. And with that, I will stop and thank you for your attention.
Thank you very much, Brian and Steve. We have time for questions. And thank you for leaving time for questions. Priya has her hand up.
Hi, hi everyone. Really great talk, and I really love how Brian and Steve have showed you can get to actionable insights even when you have a very diverse user population. And I think that this is very interesting work and very valuable work. So I'm with HPE and part of Ray Beausoleil's integrated photonics group. My colleague Bassem is on here as well. And as our group is pretty active with the hybrid photonics. So one of the questions that I had is, in order to be able to use Exensio, and you've started with the edge tools, do you need to have an MES system in place, or can you operate in a standalone fashion? That's the first thing. And then the second thing is, given your success with the edge tools, what's your thoughts in terms of the next set of tools that you'll be extending this to?
Well, so we don't have an MES system at UCSB. So I'll let Steve maybe comment a little bit more on that particular aspect of that question. So the answer is we don't. We can use these as standalone systems. Okay, so with the success we've had, so the next systems, we're putting in a couple more systems under this program. We're going to be putting on PECVD systems, which we're doing right now, including a low stress system. We really need some controls there, better controls. And we're going to be integrating with one of our sputtering systems and with some rapid thermal processing systems. So we're just beginning to expand into the realms where we can begin thinking about, with good control over lot names, recipe names, and these things, being able actually to track more of a whole process flow, at least with a number of tools within that flow.
Awesome.
Did that answer your question?
Yes.
Okay.
Steve, do you want to add anything, or I could?
No, I just want to say that definitely in the large standard facility, there is the MES that helps you tie the different data types together, things like wafer ID or lot ID and whatnot. And here, one of the challenges was really the fact that that the MES system does not exist. So that means that it creates a whole set of requirements of how the nanofabs manage the data and how they enter the outcomes of those recipes, such as metrology. And so it requires a certain discipline due to the lack of the MES, but it's very exciting to see that the nanofabs are actually able to nail it.
Agree with that. Thank you so much.
Welcome.
We have another question.
Yeah, I would like to ask if I can, Steve.
Please.
And I'm just looking for a number, Brian. I'm looking for a number. You mentioned how you had issues, and even for the one user. General question: without Exensio, without the data, the errors you found. One, would you have found it without it? That's a general question. And how long would it have taken?
Those are tough questions. So the answer to question one is maybe. So it's I think some of them probably with deep digging and a lot of time, we could find things. And the second part again was how many?
How long?
Oh, how long?
Yeah.
Yeah, well, I think I kind of answered that. So historically, we've had some problems that have taken us weeks to figure out that we believe that the software has really helped. It turns it into hours a day instead of weeks. So
can I add to that there are also, this is Demis, I also work with Brian, that there are some problems that like some of these problems are so complicated and you have hundreds of sensors, you don't even know what to look for. I think there are lots of these problems that we never would have solved. We would have never found it, because if it takes 3 weeks of data analysis to look at it, you never have that time. So I think there's a good number of these problems that literally would never have been solved. You just say, sorry, that's life in the lab. And so we're actually able to improve the repeatability and outcome because of this data analysis. I think there's some of these problems that we were just told the user to live with it, basically.
If we can come up with some numbers for an example or two. I know it's hard, but our sponsors would be interested if you have any way to come up with some quantified examples. We would love the opportunity to pass those along. Other questions?
I have a question for Steve. Steve, what is the minimum number of tools from a nanofab point of view that you require to bring the yield? So the yield is device yield, or from a wafer standpoint, better.
Yeah, it's an interesting question. A lot of times you don't know what is the step that is limiting your yield. Sometimes it's an interaction of multiple different steps. So that's the reason why in a commercial fab, you will see that the FDC, the fault detection and classification, is done on 100% of the tools. And so it's absolutely critical to have it, because even if you have an FDC for the tool that is a yield limiting tool, the fact that you do not have an FDC for the other tools will always leave a suspicion that maybe actually I didn't catch the real problem. Maybe the real problem is somewhere else. So I would say that it's absolutely critical to have all the tools feeding the trace data into the centralized system and be able to analyze across the entire manufacturing flow.
A follow-up question is, did you think about creating a test structure that can be utilized for simple flows in a nanofab?
A simple test structure?
Yeah, simple test structure.
Yes. So I'm not going to take the credit. Actually, that was done by Brian's team.
Okay.
They actually did come up with the special coupons. And so, Brian, maybe you can answer the question.
I missed the beginning of the question.
So yeah, go ahead.
Go ahead, Steve. So
yeah, so I think the way I understand Ajay's question is that if we thought about creating a special structure that would be used to characterize the process. So maybe you can speak a little bit about the coupons that you designed, and now you actually are sharing those coupons with the other facilities.
Right. So for the etchers, we use coupons, and so there were some things that were very, very important about doing coupon-based etching. If you want to look at reproducibility, one is making sure they're always exactly the same size, making sure they have the same exact patterns on them, making sure we are measuring the same spot on each pattern, making sure that the area of material you're etching is the same every time. And so we took a lot of time just developing operating procedures for making those coupons, and then for so that's reproducible. So that's really from us. So that may have not answer your question from our context, maybe not from a general context.
So the question will go back to Steve. I mean, Steve, I was thinking about a test structure that goes through the entire flow from a nanofab point of view, which would be a simple test structure. Let's say you're creating a diode, and diode is probably sufficient enough to cover a spectrum of tools there. Have you thought about such a test structure where you can have the scribe lines, etc., on the test structure?
So I have a partial answer for you. We definitely had a lot of discussions about this, and one of the things we were trying to do is come up with characterization vehicle, and we actually do have the projects that are sponsored by California Dreams, and so the intent of those projects is actually to demonstrate a full flow. So the idea would be, and that's where we are getting over the next year. I don't know if Brian, you want to say a few words on this, but the intent is exactly what you said. The intent is to pick one of those projects with a full flow and try actually and put together the analytics for the full flow. This is essentially what how most of our customers are doing it in real operations, right? And the intent would be to do something similar here.
Yeah, absolutely. But you don't need the full-fledged flow. I mean, you probably can carve down into a few tools that is very critical for that particular test structure, which can monitor at least majority of the tools, or the minimum number of tools.
Absolutely, yes, I agree.
Thanks.
Okay, we have a question in the chat window. Jude, do you want to ask your question, or would you like me to read it?
Yeah, hi. Yeah, this is Aju from University of Colorado Boulder. Yeah, I'm curious to know what's the is that a program? Can other university and Nanofab participate in this? And what's the cost?
Steve, I think you are best suited to answer that one because we have a limited number of members within California Dreams, but one of the things we've been discussing actually at the beginning of the program, how can we make it available to people in the other hubs outside of California Dreams? Maybe you have an idea of, I mean, I think it's hard to tell the cost here without knowing the particulars about the nanofab. For example, what are the tools, what kind of data is collected in the log files, what are the means of getting it out. So we actually went through a long process of scoping out the current facilities, the current nanofabs, and we would have to do something similar. So without this kind of a study, it's very hard to say what the cost is going to be. But maybe Steve, you can comment on the general idea of how a nanofab could engage actually with us, if it's through California Dreams or somebody else.
Yeah, I was thinking you were the right person to answer that question, but what I can say is since Colorado Boulder is outside of our hub, you're welcome to engage directly with PDF. We can share email addresses if it's okay with Steve in the chat window.
Absolutely,
Happy
yes.
to have somebody from Dreams involved in that discussion if it's helpful to pass along experience or to think about how to integrate this into a broader ecosystem. But you're also just welcome to engage individually.
Okay, thank you. Yeah, I think a contact number at PDF, that'll be useful. Thank you.
Do we have time? We have time for maybe one last question if anybody else has one. Otherwise, we can wrap up. We don't have another question. Let's thank Steve and Brian one last time for today's excellent seminar and for all the good work that you're doing within our hub. I see some thanks coming in the chat window, so thank you for those. And Steve and Brian, don't forget to watch those and the appreciation people have for the good talk that you just did. Next week, we have John Hacker from Teledyne. The week after that, Subu Iyer from UCLA. May 16th, another speaker from UCLA, Chi-Wei Wang. We're taking May 23rd off for the Friday before Memorial Day, and then back on May 30th with Min Nguyen from HRL. On the previous slide, we have a QR code that you can use to get information about our seminar series. Most of you have probably found that if you're on today. Some of you watching on YouTube, this may be new to you. And if you are watching us on YouTube, please like and subscribe. We are up to 69 subscribers on our YouTube channel. So I know many of you who are watching live are not yet subscribed to our YouTube channel because we've had a lot more live attendees than that. But we also have over 1,500 views of the videos on our channel that have archived all of these live seminars. So we're very grateful that we're able to reach such a wide audience with these talks. So thank you, everybody. Thanks again to Steve and Brian, and we'll see many of you next week, I hope.
Thank you, everyone.
Thanks.